And he has been at Arizona State for a number of years, and he works in dynamical systems. He's done some really important work in dynamical systems generally, but also in particular in applications to atmospheric sciences and so on recently through his work on data assimilation. And he's going to start explaining that to us today. So, but with okay, with some introduction to dynamical systems and so on. So we're really pleased that he was willing to do this and work it this way. So Amit wants to make one quick announcement. So
just about notes. So
yeah,
who will be taking notes? Just wanted to make sure. I have the list, but I didn't see it. So okay, good. Thanks.
Yeah, we got people taking notes from you, Eric. So.
And I will
okay, very good.
Okay,
well, I think Chris, you and Amit both have a copy of the slides, and so now I can't see you when I'm sharing the screen this way, but please, if there are questions, if Amit or Chris, if you would let me know, and I can stop, and I would be happy to answer. Now, I think this is scheduled for about 75 minutes. Is that correct? Yeah, okay. All right, I think this talk is maybe about an hour or a little more, but I thought if there were questions, there would be plenty of time, for discussion afterwards. So I'd like to begin by thanking Amit and Chris for inviting me to talk with you today. It's really a pleasure. I'm sorry I can't be there in person, but anyway, this will be part of a 2-lecture series. Today is more of an introduction. I hope for those of you who've seen some of this before that you'll bear with me. For those of you who maybe have not seen some of the mathematical theory, I hope it will be useful without being overwhelming. So with that, let me go ahead and begin. Let's see here. Here we go. So this work is actually been a joint effort with a large number of collaborators. There's really too many to thank, but some in particular who have made very important contributions here are Istvan Sunyog and Eugenia Kelme, who were both at the Department of Atmospheric Science at the University of Maryland, and also Brian Hunt and Ed Ott, who are a mathematician and physicist, respectively, in the Institute for Physical Science and Technology. They hosted me for a couple of years, actually, while we got started on this work. And of course, Jim York and many others. Our funding has come from National Science Foundation, from NASA, and I'd like to acknowledge ASU for some support on a sabbatical leave. There are a couple of websites. The main one here for some of the papers is the Weather Chaos website. UMD is the University of Maryland. And then my own webpage, which is not so fancy graphically, but there are some MATLAB codes there that you'd be welcome to download, and also some slides from a previous summer school that was held in 2008 at the Mathematical Sciences Research Institute at the University of California at Berkeley. There are some papers here that are of interest here. Again, you can get these from the Weather Chaos website. There are a number of papers on that website, but two in particular that I would like to call your attention to are this paper by Brian Hunt, myself, and Istvan that appeared in Physica D in 2007, and this describes the derivation and the motivation for the local ensemble transform Kalman filter. This is a somewhat more computationally efficient version of the original idea that was published by Ed Ott and the rest of the group in TELUS back in 2004. The paper in 2005 describes the performance of this data assimilation system in the presence of what we call a perfect model scenario. I'll talk about some of these results more tomorrow. And then finally, we have a paper that appeared in 2008 that describes a fair number of experiments with the global forecast system, that's the U.S. Weather Service's global forecast model, with real data. And again, I will give you more details on all of that tomorrow. So the outline of the lecture this morning is really three basic parts here. One is to talk a little bit about some of the theory of ordinary differential equations, and in particular what that means in terms of predictability. We'll talk a little bit about chaos and really what we mean by chaos. And then finally, I want to introduce this notion of ensemble forecasting, and what's especially important is this notion of what we call local low dimensionality. This is the ingredient that makes much of our data assimilation work actually operable in a large model. So to start here, this is just a little bit about ordinary differential equations. Now, the equations for the atmosphere are partial differential equations, in particular the Navier-Stokes equations. The mathematical theory for partial differential equations is much more elaborate than for ordinary differential equations. But on the other hand, when you discretize a model, or discretize a physical domain, often what you end up with is a large coupled system of ordinary differential equations. And so this is theory that one might think of as being applicable, at least in principle, to a computer model that has been implemented on a discretized domain. So what we're thinking of here is we're looking at equations where the rate of change of some vector vector of components here. So this might be a state vector for the atmosphere, or it could be the state vector for some chemical experiment, whatever. But that is a function of both the current state and time. So in a population model, for example, the birth rate, maybe this is the rate at which new individuals appear in the population, might be some function of the current population, but also of the season. So if you had a bunch of insects, and if time is in the fall, maybe the population isn't growing because it's getting cold and the insects will soon die off, but the same population in the springtime might be growing very rapidly because of favorable weather conditions. What we mean by an initial value problem is simply that at some starting time, we specify all the components for this vector. And really finding the initial conditions here when we're thinking in terms of a numerical weather model is really half the battle here, because it's one thing to try to figure out, well, what is the best model for the atmosphere, but in order to run this model on a computer, we have to specify numbers, we have to specify every component of that starting vector, but we might not necessarily have measurements that would support putting in a particular number, so we have to infer or guess some of the components of this vector. And so the question of how you do that in an accurate way, of course, is really the subject of the entire summer school, but I will talk about one particular approach to answering that question in tomorrow's lecture. So what we mean here by a continuous function is that if you change x a little bit, then f of x changes a little bit. And what we mean by a Lipschitz continuous function is that if we take x and y as points near some starting point, so near, let's say, some initial condition of interest, then if we look at the distance between x and y, okay, these are two different points that are perhaps close together, then what Lipschitz continuity means is that the images of x and y under our function will also be close together. The distance here can be stretched a little bit, but they can't be stretched indefinitely. There is a bound called the Lipschitz constant L that says that if x and y are close together, then so are f of x and f of y. They can't multiply distance by more than some factor of L, at least for points x and y that are sufficiently close to x naught. And so from a theoretical point of view, this is what you need to guarantee the existence of a unique solution of a collection of ordinary differential equations. And so what the theory says is that once you have specified your initial conditions, there is exactly one solution, and that solution actually exists for some interval of time around your starting time. Now, the details here depend a little bit upon your neighborhood and also upon your particular dynamical model, but nevertheless, what this is basically saying is that if you know your initial condition perfectly, then at least for a little while, you are guaranteed to be able to make a prediction. There's a unique solution. So one implication here is if you know your initial data perfectly, then you know the future perfectly. Now, of course, the reality is that you never can measure a given point exactly, and so although this may be sort of the true state, let's say, of the atmosphere at this moment. We'll never know that exactly, but what we might hope to do is have some approximation of that we've obtained by some means. And so there will be some error necessarily between our approximation and the actual truth. Now, you might wonder, well, maybe this is a complete and total disaster. But the answer is not really. There's another theorem called Gronwall's inequality that basically bounds the rate at which errors can grow, at least for a while. So if this is our initial error in the initial conditions, then as we run two different solutions, here's maybe the true solution, here's our approximate solution, the distance between those two can't grow faster than exponentially, and the bound is given in part by this Lipschitz constant L. So they're never further apart than the initial distance times some exponential value. Now, this is really the best that you can do in general for sort of an arbitrary F, an arbitrary continuous vector field F. This is the best you can do. And the reason it's the best you can do is you can imagine here, if we're just on the real line, F of x is simply, x here is just a one-dimensional vector. In other words, it's just a scalar number, L. So if F of x is actually equal to L times x, then this equation here is simply the exponential growth equation, and as you all know, the solutions of this equation are simply e to the L times t, if we're starting out here at t not equal to 0, times some initial number. So that means that if we're looking at the exponential growth equation, our true value is x naught, our approximate value is x naught hat, then the growth in the solutions is the initial error times e to the LT. So this is a case where this less than or equal to in the Gronwall's inequality becomes an exact equality here with t not equal to 0. So in general, you can actually hit this bound for the exponential growth equation. And that's what I mean when I say that this is really the best possible estimate. So now in thinking about the problem of, weather forecasting, climate forecasting, ocean models, and so on, one of the things that can beset any such effort is that there is potentially here, exponential growth of errors. All right, so that's why I say this is a hint of the difficulties. Uncertainties in initial conditions can amplify exponentially in time. Now, the details of exactly how fast or even whether they amplify exponentially in time really do depend very much on the details of the equations. So, for example, here is the exponential decay equation. So I've put, it's just like the other one except that I've inserted a minus in front. And so what happens here is that solutions are exponential, but they're e to the minus lt. We think of Lipschitz constants as being positive, and so this is a decay term. So in this very simple case, the distances between every pair of solutions tends to zero as t goes to infinity. I'm sorry, that should be an infinity rather than a zero. So so in this particular type of equation, all of your errors damp out. So what we're worried about are cases where, as in the previous slide, initial conditions can separate exponentially in time. There are other cases where initial errors damp out, and maybe there are cases where we're somewhere in between, and so we're sort of worried about circumstances under which these uncertainties can grow. So the next level of sophistication, if you will, in our analysis here is to think about linear systems of differential equations. And in the simplest case, these have constant coefficients. So now we have a system of first-order differential equations where all the coefficients in front of the components of x are simply constant. So we'll think of A here as some constant matrix, n by n matrix, and furthermore, for the sake of simplicity here this morning, we will suppose that this matrix A has n distinct real eigenvalues. You can deal with this situation with repeated or complex eigenvalues as well. But for the moment, let's just suppose this matrix has n distinct real eigenvalues. So we have a full eigenspace, and because all the eigenvalues are distinct, that means that all the eigenvectors are distinct. And so given an initial vector of initial conditions, then we can simply write that solution as a linear combination of the eigenvectors. So V here, V1 through Vn are the eigenvectors corresponding to the eigenvalues lambda 1 through lambda n of this matrix A. So it turns out that it's possible, given any initial vector, that we can write this as x naught times some sort of a matrix exponential. And so in particular what that means is that this is a linear combination of each of the eigenvectors times the exponential to the appropriate eigenvalue, and then there are some constants, C1 through Cn in front. The C1s through Cn's depend upon the details of x naught. Okay, so the idea here is that if you change basis, so that we write our initial condition in the basis of eigenvectors, then we can write x naught in particular as some linear combination of v1 through vn. So in particular, when t is equal to 0, each of the exponential terms is just equal to 1, and so x naught is equal to c1 v1 plus c2 v2 and so on, and that's precisely what we mean by this particular notation. So the nice thing about linear systems with constant coefficients is that given any initial condition, we have this relatively simple formula that describes every possible solution. Now, what this also means, however, is that if any of these eigenvalues are positive, so for example, if lambda 1 is positive and there is some error in the first component of x naught, then the distance between x naught and, let's say, x naught hat will grow exponentially according to e to the lambda 1t. So what we would have here, the distance between x naught and x naught hat, might be c1 minus c1 hat. That whole quantity would tend to grow with time if we had a positive eigenvalue. Okay, and so this is a global result because I can write every solution, in these terms. Now, when we talk about nonlinear systems of differential equations, this is a much more complicated situation. There's really no general formula for writing down a solution x of t of some sort of system like this. The best that you can do is to look at cases where you have a fixed point, and x naught is a fixed point if f of x naught is equal to 0. So if x naught is a fixed point, f of x naught is 0, that means x prime is 0, which means that your system isn't changing when you start at the point x naught. That's what we mean by a fixed point. Now, what we're often interested in, of course, is that in the real world, it's very rare that we could start exactly at x naught due to noise or a measurement error or something else. We will start not at x naught, but at some nearby point to x naught. And then what we can do is ask what happens to solutions that start near the fixed point as time goes on. Now, one classification of this type of system is, or this type of fixed point, is that we say it is hyperbolic if, when we look at the Jacobian matrix, that is, the Jacobian matrix is the matrix of partial derivatives of this whole vector-valued function. So if f has n components to it, then the Jacobian matrix is an n by n matrix. The first row is the gradient of the first component of f. The second row is the gradient of the second component of f, and so on. So this becomes now an n by n matrix. So since it's an n by n matrix, it's going to have a collection of eigenvalues, and if all of those eigenvalues are real and non-zero, or if they're complex and have non-zero real part, then x naught is said to be a hyperbolic fixed point. And so when you have a hyperbolic fixed point, this is a very nice situation because there's another theorem that applies to this case called the Hartman-Grobman theorem. There may be other names attached to this, but these are the two that I know. And so what the Hartman-Grobman theorem says is that when you have a hyperbolic fixed point, there's a change of coordinates that, at least locally, near x naught, there's a change of coordinates that maps solutions of my original differential equation onto solutions of a linear differential equation where A is this Jacobian matrix associated with f, and it's evaluated at the fixed point x naught. So what the theorem says is that if you have fixed points in a nonlinear system, then in some neighborhood of those fixed points, everything looks like a linear system. And so this means that at least for some period of time, you can say something about what the solutions will do near that fixed point. And what I'll do now is give you some explicit examples of this. Okay, so there are three basic types of hyperbolic fixed points. The simplest one is a sink. And the idea here is that things drain, of course, into a sink. And so a sink is the case where all these eigenvalues are either negative or have negative real part. And as the name implies, all points near a sink eventually drain into the sink, so a sink is an attracting point. At the opposite end of the scale here is we have a source. This is the case where all the eigenvalues are positive, or they have positive real part. And so what that means is, just like water bubbling up from a spring, all initial conditions near the fixed point eventually flow away from that fixed point. In between, we have something called a saddle. And a saddle has a combination of both negative and positive eigenvalues, or eigenvalues with either negative and positive real parts. And so when you have a sink, then, because everything is flowing in, sinks are very stable. They're insensitive to small initial errors. We can certainly predict what's going to happen to a sink. If you start close to a sink, you will flow into the sink, and then you will stay there because the sink is a fixed point. But if you have a saddle or a source, anywhere that there's some positive eigenvalue or some eigenvalue with a positive real part, then you're going to have exponential growth or exponential separation of solutions, at least for a little while. And because there's going to be exponential growth in some component, then that means that that fixed point is unstable. It's what we call a sensitive point. If you start anywhere sort of near that, typically if you start near that point, you will tend to move away from that point. So that's what we mean by sensitive point. So let me illustrate this with a simple example where we have a damped nonlinear pendulum. So you all have studied the case in calculus or differential equations where we have acceleration, some sort of linear friction, and in the textbook case that you learn as an undergraduate, we suppose that we're starting near a fixed point so that sine x roughly equals x, and so we get rid of the sign here and we just write this as x double prime plus some constant times x prime plus perhaps another constant times x, and it turns out that it is possible to write the solutions x of t in terms of sines and cosines typically. So if you think of a grandfather clock, this would be periodic motion, potentially with damping. All right, now if you suppose that the pendulum is no longer going to be a small angle away from the vertical, maybe instead of, so here's our pendulum at rest, it's up and down. Instead of starting at a small angle, maybe we allow for perhaps quite a large angle from the vertical, then we would replace x with sine x, and that makes it a nonlinear pendulum. The superposition principle doesn't necessarily hold here. Now when we have friction, we're going to suppose that k here is some positive constant. Now, you'll probably also remember from your differential equations course that any second-order system of equations can be rewritten as an equivalent first-order system by defining x1 as position. That is, if we think of x as the position of this pendulum, let's say in radians or something from the horizontal, or from the vertical, then x1 is position, so that's x, and then x2 would have the interpretation here of velocity, and so what would happen here is that x double prime is going to be x2 prime, and so this is how I can write it. So here's x double prime is x2 prime, and then moving these other two terms over to the right hand side, I have minus k times x prime, but x prime is x2, so here we go, and then x1 is x, so here's minus x1, and we also, the first equation follows from this definition that x1 is position and x2 is velocity. So this is the equivalent pair of first order equations that's identical to this initial second order differential equation. Now this first order system is a little bit more convenient to work with because when we ask about what are the fixed points, we simply have to make the right-hand side here equal to 0. So a fixed point would certainly be the case where the initial velocity is 0, but also where the initial position is 0, because of course the sign of 0 is 0. So that position would be basically down. So if our pivot is here, this thing is hanging down just like a grandfather clock that has wound down. So that's this first fixed point. Okay, now the other possibility, of course, is that x2 is still 0, but another value of x1 that makes the sign equal to 0 is the case where x1 is equal to pi. And this would be the case of a pendulum that is starting straight up and down. So if you had a perfectly balanced pendulum, basically hanging straight up, then that would be a fixed point. That pendulum would not move. But of course, your intuition here is exactly the right thing. If I perturb a pendulum that's hanging straight down, and I just give it a little push, the pendulum will oscillate just a little bit, but then it'll eventually come to rest. And that's true of any initial push. Okay, it doesn't really depend upon the details very much. Your pendulum is going to oscillate for a little bit and come to rest. Now, on the other hand, if we've got a pendulum that's hanging straight up, and you hit this pendulum either from the left or from the right, no matter how small that perturbation is, the pendulum will topple over. And depending on the details of what your initial push is, it will topple over either to the right or to the left. So this is a sensitive point, an unstable point. All right, so now how does that intuition translate into a rigorous mathematical analysis? Well, the Hartman-Grobman theorem says that, well, we should linearize our system of differential equations. And then if you take that previous set of equations here and you calculate the derivative with respect to x1 and then the derivative with respect to x2, the gradient of this first equation is going to be 0, 1, okay, because the derivative of x2 with respect to x2 is equal to 1. The derivative of this right-hand side here with respect to x1 will be the cosine, and the derivative with respect to x2 will simply be k, and that's basically what I have over here. So this is the Jacobian matrix. Now, if we look at the fixed point at 0, 0, this corresponds to our pendulum hanging straight down. Of course, the cosine of 0 is 1, and I've got a minus sign in front, so this is my Jacobian matrix at this nice stable fixed point. And the reason I can conclude it's a stable fixed point is that if I do the calculation and I ask, well, what are the eigenvalues of this particular matrix, then a calculation shows that the eigenvalues are given by this formula. Remember, when you solve for eigenvalues, you're actually solving a quadratic equation in the case of a 2 by 2 matrix, and this is basically following from the quadratic formula. Now, what happens here, of course, is that the square root of k squared minus 4 is always going to be a quantity that is less than k in absolute value. So whether I add it or subtract it, this numerator here will always be a negative number. And so all the eigenvalues here are necessarily negative, and so 0, 0 is a sink. So if you push the pendulum of a wound down grandfather clock, it will come to rest, and so that's stable. Now, on the other hand, if we look at our pendulum that's bound straight up, one that's likely to topple in each direction, we can observe this analytically by doing the same calculation now with x1 replaced with pi. So so in other words, if x1 is pi, this term of minus cosine x1 becomes minus negative 1, and so we now have a plus 1 instead of a minus 1 here in this lower left-hand element. And so now when we calculate the eigenvalues, instead of having k squared minus 4, that now turns into k squared plus 4. So the square root of k squared plus 4 is always a number that's bigger than k in absolute value. And so when I add such a thing to minus k, this quantity will be bigger than negative k in absolute value, so the numerator will be positive. And of course, when I subtract the two, I've got something that's negative, and so my eigenvalues then straddle 0. I've got a negative eigenvalue and a positive eigenvalue, and so this is a saddle, and therefore a sensitive point. So what this means, of course, is that if I give this pendulum a little bit of a kick, then it might stay upright for a little while, but eventually it's going to topple over, and that that growth rate, at least initially, is exponential. So obviously it doesn't keep moving. The acceleration does not grow exponentially forever because this pendulum would come to rest obviously in the straight up and down position. But all this means is that the initial velocity grows exponentially in those first few moments after it begins to topple. Okay, so now the question is, well, if you're trying to measure an initial condition that is perhaps near some fixed point, or maybe it's not even near some fixed point, but we've got some error, so maybe we think of this as being an underlying probability distribution function for some, for some error term about our measurement. Then the big question is, how does a dynamical system propagate the uncertainty in such a case? So. So we can look at that. So one of the tools that you can use is, again, linear analysis. And so the basic formula here, and maybe they don't necessarily cover this in linear algebra so much, but it's a surprising. It's a very nice fact, I would guess. Perhaps you find it surprising, but if you think of a circle of points. Maybe this is the unit circle, and you think of each point on that circle as being a vector, so the tail is at the origin and the tip goes to some point along the circle. So we've got this collection of vectors whose tips all generate the unit circle, and you multiply all those vectors by the same matrix A. Turns out what you get is an ellipse in general. And so this ellipse idea is really the geometry behind the singular value decomposition, which I think you all have looked at a little bit. And so one of the big theorems in linear algebra is that you can take a general n by n matrix and you can decompose it in a way such that we have a diagonal matrix here in the middle, and then a collection of left singular vectors and right singular vectors in a way that often gives us very useful information about how either the rows or the columns of this matrix are spread out in some either m or n-dimensional space. So the definition here is that the singular values are, by definition, the square roots of the eigenvalues of A transpose A. Now remember, given any matrix A, A doesn't have to be square, but if you take A transpose times A, that's always well defined, and this will always be a square matrix. So if A is n by n, then A transpose is n by m, and so this product here is an n by n matrix. And this is necessarily a symmetric matrix, and because it's symmetric, all the eigenvalues are real. And so then I can, and in fact, not only are they going to be real, but they're going to be non-negative, and so I'm safe when I talk about the square roots of those things. So by convention, we order the singular values so that S1 is the largest and Sn is the smallest. As I said, singular values are always non-negative. And a geometrical interpretation is that if your initial set of vectors generates the unit circle, then if I multiply each of those vectors by the matrix A, I will get an ellipse, but the ith major or minor axis of that ellipse will be equal to the corresponding singular value. So let me show you how this works in the context of the damped nonlinear pendulum. So we'll take a specific value here of k. We'll take k equal 2 just to make all the numbers come out nicely. So here's our initial equation. Okay, let's consider the unstable fixed point here. So our previous analysis showed that the eigenvalues were given by essentially the quadratic formula, and now we're going to say that k is equal to 2. So if I plug in k equals to 2, the eigenvalues are now -1 plus or minus the square root of 2. So lambda plus is certainly a positive value, lambda minus is a negative value. Here's the Jacobian matrix that these eigenvalues belong to. Okay, so now if I take this particular Jacobian matrix, that's A, and now if I imagine, okay, now I should tell you, I've turned the picture sideways so that it fits on the screen, but here at the center of your picture is the point x equal to pi and y equal to 0. As I said, I've taken the original picture and turned it turned it 90 degrees clockwise so that it fits on the screen. So I'm going to imagine an epsilon neighborhood of my unstable fixed point here. So my initial position is pi, my initial velocity is 0. I'm going to ask what happens to the points nearby when I multiply them all by this particular matrix, which is 0, 1, -1, -2. So if I take that matrix, I call that A, and I multiply every point here on the blue circle by the matrix A, then I get this nice red ellipse. So what I'm saying here is that if you look at the actual singular values, and if you do this calculation, you ask, well, what are the square roots of the eigenvalues of A transpose A? Turns out that those are going to be 1 plus root 2 and square root 2 minus 1, and so the approximate numerical values here are 2.4 and 0.4. So what we have here is a major axis, S1, whose length goes from epsilon to 2.4 times epsilon, and another minor axis which shrinks from epsilon down to 0.4 times epsilon. So the ratio between these two numbers is roughly 6, and so that means that the minor axis, the ratio of the minor axis to the major axis is 1/6. So this is 6 times longer in this direction than in this direction. Okay, so if we think of more abstractly now as what happens to a collection of measurement errors. So maybe we're trying now to empirically measure the position of a pendulum. So maybe the truth is exactly at pi 0, but due to measurement error, we could be basically anywhere here in the circle. If we think of the circle as our probability density function for the error, then the dynamical system over a period of time is going to stretch that error in one direction, compress it in another direction, but there's going to be directions along which things are sensitive. That is to say that our initial uncertainty in the state is going to become amplified in some direction. Okay, and this is a property that seems to be pretty general in the case of the weather and many other types of geophysical models, that there are lots and lots of initial conditions. In fact, for a typical initial condition, this seems to be the case. Now, of course, when you're dealing with a large weather model, your state vector may consist of hundreds of millions of components, and so this would be rather hard to visualize, but still, from an abstract point of view in some mathematical space, what's happening is that there are at least some directions in which the initial uncertainty is being stretched away from the initial point, and others in which it is being compressed. So there is amplification of errors in some directions, and some directions in which the error is actually shrunk, okay, in ways that are in general pretty complicated. Now, when you when you have a nonlinear system, even something as simple as this pendulum, and now you force it instead, then when you force this pendulum enough, at a high enough rate of forcing, the behavior becomes chaotic. And one of the defining properties of a chaotic process is that essentially every point is a sensitive point. So every point has this property that uncertainty gets amplified in at least one direction. And so that means that if you have uncertainties in initial conditions, they're going to grow. And in fact, they're going to grow exponentially to start with. And because of that, things are rather hard to predict. So what this means is that exponential growth of errors eventually swamps your calculation. Now, the process itself can be perfectly deterministic. What I'm talking about is where you have errors or uncertainty, let's say, in the measurement of an initial condition. So even though we have something that's perfectly deterministic, like a simple four-stamped nonlinear pendulum, if you have error in the initial condition, then you might not be able to predict the future position and velocity of that pendulum for very long into the future. So this is the idea, the mathematical idea that motivates this notion of ensemble forecasting, and you'll hear quite a bit about this in the coming days of the workshop. But essentially what we're trying to do now is, if you have a really big model, something that's got millions of variables in its state vector, then it's not practical to calculate all the eigenvalues and eigenvectors of the Jacobian matrix, let's say, at any given point. So what we have to do here is to try to figure out in some computationally tractable way what's happening to our circle of uncertainty in some space that's containing the state vector for our model. Now, one way you can try to do this, if your model isn't too terribly complicated, is you can integrate what are called the variational equations. So I start with an orthonormal matrix whose columns are are sort of spanning my initial circle of uncertainty. Then I integrate the Jacobian matrix of that, and this is called the variational flow, for example. But if F is a weather model and F has maybe 100 million components to it, then DF in principle is a 100 million by 100 million matrix. That's just not something that you're going to integrate in any reasonable amount of time. So this is either too hard to do or it's computationally intractable. And so, but this is essential if you're trying to figure out how fast uncertainties are propagating, or how fast the uncertainties are growing with time. So because this is in general too difficult a problem to do on a computer, we will resort to a simpler procedure in which we try to integrate in what we call an ensemble, how fast my uncertainties will grow. So basically what's happening here is that ensemble forecasting is in its essence a Monte Carlo method. Now remember, Monte Carlo, what we're thinking of here is something where you're throwing darts at a dartboard, you're rolling dice on a table. We're treating everything associated with this model as a random variable. So we don't know our true state vector. Instead, we have a measured state vector. That measurement has some probability density associated with it because all these things have random noise associated with it. So what we want to try to do in this data assimilation idea is to find some initial condition that represents a best guess, and one way of doing this is through maximum likelihood, for example. So we're going to take our best guess, we're going to take some nearby initial conditions relative to some norm. We're trying to take somehow nearby initial conditions that we hope sample the estimated error covariance of that best guess, and then basically integrate all these things. Now, in order to make sense of all of this data, we have to have some method for visualizing it. And in the case of atmospheric science, what people use are called spaghetti plots. This is a highly technical scientific term you have to understand. So here's a picture of what I mean by a spaghetti plot. What you're looking at here are a couple different contours of what is called geopotential height. These are what's plotted here are locations at which more or less we're at the 500 millibar pressure level. This is a point at which half the atmospheric mass is below this level and half the mass of the atmosphere is above this level. If you are not acquainted with this term and you don't know what geopotential height is, then for our purposes today, you can simply think of this as a forecast location for where the jet stream will be, let's say 48 hours from now. So this is a typical 48-hour forecast. Now this really isn't showing the jet stream, but for purposes of just trying to understand the flavor of this, it's good enough to think about it in those terms. So this is a forecast over North America that was started, let's say, last March. And so that's late winter, early spring. We're right at the spring equinox at this point. And so this is a forecast for what these variables will be 48 hours hence. And one of the things that you can see here is that each of these blue curves here is a statistically equivalent forecast 48 hours hence of what this particular variable or what the position of this jet stream will be. Now, over here, south of the Aleutian Islands, all the curves are pretty close together. And one of the things you can conclude from that is that, well, with pretty high confidence, I mean, assuming that we've sampled our forecast uncertainty pretty well, then we have pretty high confidence that 48 hours from now, the jet stream will be, let's say, in this position over here in the North Pacific Ocean. But over here off the northeast coast of the United States, it's a different situation. Many, but not all, of the blue curves are forming a circle here, and basically what the circle represents is a low pressure system, what's often called a nor'easter in the northeast in New England. And a nor'easter, there's cyclogenesis, so storms tend to spin up along the eastern coast of the United States. And so these are storms that bring a lot of wind. They can bring quite a bit of snow, or freezing rain or rain, but this can be very disruptive both to shipping and to airlines, and they can be pretty miserable weather for people who live in Boston and New York and places like that. On the other hand, there's not unanimous agreement here, see? So some of the curves suggest that there's not a nor'easter, and so one of the questions then, if you're a forecaster, is, what probability do you assign to the likelihood that there's actually going to be a nor'easter, 48 hours hence. So if maybe 70% of these curves here are actually going into a circle, then maybe you conclude that there's a 70% chance of a nor'easter spinning up along the coast. Now, one of the other problems is that because the weather is chaotic, these uncertainties tend to grow and grow with time. And so what I will try to do here is, just for the moment, since I'm sharing the screen, I hope this is going to work. I'm going to exit out of this. And I'm going to go over to my other screen where I can see you all. You're not all asleep, which is good. Let's see here. So let me see if I can show you here. Try to move this all out of the way. Can you see this map here? Okay, maybe I can move this closer. And can you see this better now? I'll try to move this window out of the way. Okay, all right. So this is the current operational system that's been running at the National Centers for Environmental Prediction, and so this is a forecast starting at 6 p.m. Greenwich Mean Time on January the 5th. So this is the latest model run that I was able to find prior to the lecture. And what we're seeing here are, again, these level curves of geopotential height, or what you can think of, if you like, as the jet stream. And what we're seeing here is the best guess for what the current state of this atmospheric variable is over Canada. Now, what I'm going to show you here is an animation. This will run out for 16 days of forecast time, starting essentially from now. And what you're going to see is how this chaotic nature of these weather models tends to make the uncertainties grow with time. So let me try this here. Let's see if I click Start. So each of the intervals here is a 6-hour forecast. Okay, so let me play this again. It'll just keep playing. So we start out with today, and then you can see the forecast time is up here by my arrow. So we have July 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, all the way up to July 21st. And so you see these curves stay pretty close together. Let's say, I don't know, up to about 3 days from now. You can see the spread is growing, but there's still some, if you will, some continuity here. But as we go on in time to the 9th, to the July 10th, to July 11th, they start to diverge. Okay, and so by the time we get maybe 10 or 11 days out, they're really sort of all over the place, and by the end of this simulation, sometime on July 21st, it's just a big tangle, a big bowl of spaghetti. Now, what this means is not that the weather model has somehow blown up. Okay, that's not what's depicted here. What's being depicted is that because we don't know the truth or the true state of the atmosphere, if we now look out 16 days hence, it's really impossible to stay with any degree of certainty, where the jet stream will be, if you will, exactly over Canada. Each of these curves is a statistically equivalent forecast. Any one of them is as likely as any others, if you will. And so what this really means is that if we look 16 days out and we want to ask, well, what's the weather going to be like over Canada, we might as well consult an almanac. Okay, we just really don't have anything that we can say in terms of details, whereas if we were to go out and talk about the weather 2 days from now, 3 days from now, or 4 days from now, we can actually say something with some degree of confidence as to what the atmospheric state will be. Okay, so this is what we mean by chaotic behavior, and of course, in this weather model there are many thousands of variables. We can't, depict this necessarily as circles and ellipses, but in some appropriate mathematical space, that's what's happening. As a practical matter, what a forecaster would say is, well, maybe there's going to be quite a bit of uncertainty here over British Columbia and maybe the Northwest Territories, 4 days from now, compared to what's happening, over Saskatchewan or Manitoba, or even over Labrador or something. So that's what I mean by spaghetti plots, and these are generated, these maps and the forecasts are updated every 6 hours, and you can get them, perhaps you can see the URL here, mag.ncep.noaa.gov. Okay, so you can always be entertained. All right, so we'll go back here to to where I was. All right, so can you all see this okay now? Yeah. Okay. Now you can? Okay. All right. So, so the key points here then are that the weather is a chaotic dynamical process, and so this means that over short time scales, your forecast uncertainty is going to grow exponentially, but the details will vary considerably in time and space. Now, Ed Lorenz gave sort of a back-of-the-envelope calculation at one time, and he said that really the uncertainty in these global atmospheric state vectors roughly doubles every 48 hours. And so what that means is that there's going to be, if this is really the case, then there's going to be an intrinsic upper bound on the predictability of the weather somewhere around 2 weeks or so, because after 2 weeks there would be roughly 7 doublings of the uncertainty. So if you have a 1% relative error now, after 7 doublings, that's pretty much become close to 100%, and so you can't really say too much about this. One remark here that I'd like to make is that, as far as I know, Ed Lorenz in 1965 was one of the first people to suggest this idea of using ensembles. And Eugenia Kelney, who was there at the conference, was one of the first people to appreciate the great value of these ensembles in operational forecasting. And Professor Kelney was really instrumental in getting the operational centers in the United States and even in Europe to use this ensemble idea, and this notion of ensembles became operational somewhere in the early 90s. So she played a very important role in all this. Okay, let's see. So now, of course, this is a workshop on data assimilation, and so here's a slide about something that I think everybody knows, but as you've just seen here, if we didn't update the state of our weather model pretty frequently, then the forecasts after some period of time would be no better than climatology. So we would just consult our almanacs to see what the weather would be like. So in order for the weather forecast models to track the truth or have some semblance of the current reality, we have to update these initial conditions, and so this is what data assimilation is all about. So data assimilation is simply a procedure by which you combine forecasts with observations to come up with an updated best guess, and in the ideal case, some measure of its uncertainty. In operational centers, these updates are done 4 times a day. Now, from a mathematical perspective, of course, the kinds of questions that come to mind are, okay, so, what is a useful way of representing this forecast uncertainty, either quantitatively in terms of a computer implementation, graphically in terms of something that, we as scientists can understand, or to the general public, how you can make this notion of uncertainty intelligible. Of course, you want to make efficient use of your available data, and ideally what you would like to be able to do is to estimate cases in which there are systematic errors or biases, either in your observations or in your models. Because remember, a model is just that. It is an approximation of the truth. All models have errors, and what you hope to be able to say is perhaps where is the model likely to be wrong. Another type of question that you can ask, I won't talk about this tomorrow, but it's a good question to think about, and it's one where there's a lot of active research, and that's where extra observations might be used. So, in the United States, there's hurricane season. All the cable channels carry something called the Weather Channel. One of the well-known meteorologists there is Jim Cantore, and they always put Jim Cantore in the middle of some driving windstorm, and is, the palm trees are swaying and the wind is coming in sideways and it's pouring down rain. And Jim Cantori will talk about the Hurricane Hunter aircraft, going off into the Gulf of Mexico or wherever. Well, even if it's not hurricane season, but imagine that you had the capability, that perhaps a storm is coming. And if you work for a weather service, you could ask, well, if we had the capability of sending out an aircraft, a weather balloon, some dropsondes, or whatever, where might we take observations today to forecast our storm better that might not be coming along and that might not be hitting shore until a few days from now? So that's these are all very interesting types of questions. Now, the property that we rely on in these models, and that might not be obvious at first glance when you think about them, is this property of what we call local low dimensionality. So every weather model has millions, perhaps nowadays even a billion or so variables. And so you could ask, well, my gosh, there's so many variables here, how could I ever predict anything? And it turns out that, this is something that I thought was a bit surprising at first, but these models often act like relatively low dimensional dynamical systems, rather surprising property. And here's what I mean by relatively low dimensional. So if you take a weather model, for example, the U.S. weather model, and you run it at medium resolution, what I mean by medium resolution is that you have grid points every 150 kilometers or so. Now, and in the mid-latitudes of the world, a typical high or low pressure system is roughly 1,000 by 1,000 kilometers. So this you can think of, roughly speaking, as a spatial correlation length for the atmosphere, and these are often called synoptic regions. So think of this as typical high or low pressure system. A region that's 1,000 by 1,000 kilometers, a region that's about the size of France or about the size of Texas, okay? And so if you're running sort of a medium resolution weather model, then the components of the state vector that would describe, let's say, the weather over France is going to have roughly 3,000 components to it. So if we have a forecast ensemble of k different forecasts, and we're looking at, let's say, the weather over France, then we can think of that ensemble as being a forecast matrix, X sub f, f is for forecast here, whose dimensions are basically 3,000 by k. And so now we can ask, what are the singular values and the singular vectors of this forecast matrix? And it turns out that singular values and singular vectors are often very good ways of providing low-rank matrices that can approximate this forecast matrix pretty well. If you did the exercise, there's a picture of my dog. This is, let's say, a 300 by 300 matrix. Turns out by the time you get a matrix whose rank is, let's say, 40, you actually have a pretty good reproduction of that picture, a pretty good likeness of the original image. And so that's local low dimensionality in the context of a picture, but it turns out that the same type of idea applies to excellent accuracy for a forecast model. Now, the idea that we have in mind here is to look at a quantity that we call the ensemble dimension. And this idea is due to Brian Hunt and to Ed Ott, who proposed looking at this particular ratio. So remember, S1 through, let's say, Sk will be the singular values of an n by k matrix. S1 is the largest, Sk is the smallest, and so on. But they're all non-negative numbers. Typically, they'll all be positive. And so this is a positive sum here. So we take that sum and square it, and we divide it by the sum of squares of each of those things. Now the denominator here, the sum of squares of these singular values, is in a sense the total variance in your ensemble. It's the total variance of the ensemble vectors from the mean of those vectors. And so this is a quantity that, if you will, measures the eccentricity of an ellipse of forecast uncertainty. And so in the closing minutes here, I just wanted to give you, a picture of what this represents. So here I have a bunch of points represented by little stars here. I think there's about 100 of these points. And they're scattered about. Their mean is 0, 0. Okay, so the mean here is the center of the picture, but they're scattered all about. And if I ask, well, what is, if I think of making a 100 by 2 dimensional matrix of all of these values, and I ask what are the singular values of that matrix, it turns out that both of the numbers are about a little bit bigger than 3.5, and their ratio, this E-dimension ratio, is about 1.99. And what that means is that all these little stars here are basically filling out something that's pretty much a two-dimensional space. Now, what's actually happening here is I'm multiplying each of these stars by a particular matrix, and if I apply this particular matrix to the stars, then what happens is this distribution is now characterized by singular values of 19 and 4. In other words, S1 is about 5 times as big as S2. And this is a case where now the E dimension is 1.43. Excuse me. And so what you should think of here is that the distribution is not quite as two-dimensional as it was before. They're certainly not all lying on a line, but they're not filling out the plane as much as the original set. Okay? And now I'll go one more. Okay, so now here we have a case where S1 is about 20 times as big as S2. And so now our E dimension is about 1.1. In other words, this is a number that's a little bit bigger than 1. And in such a case, you can say, well, these points are reasonably well approximated by a line. Okay, they're more line-like than they are space filling. Okay, so here we have space filling. Okay, basically two-dimensional. Something that's in between, and something that's almost really, lying on a line. And so this is the notion of ensemble dimension, and we say that a model is locally low dimensional if, when we look at ensembles of the state factors, if they tend to lie along a subspace whose dimension is much smaller than the overall state space. So I will talk about more about that tomorrow morning. But so basically the conclusions here this morning are that you can analyze these linear dynamical systems globally. When you have a matrix, a constant matrix times a vector, and if that's your dynamical process, then we can write down in a nice simple way all the solutions, and we can say something about what happens to every trajectory. If we've got a nonlinear dynamical system, then you can do things locally, particularly in the vicinity of fixed points, but the global picture is often hard to do. A chaotic process is one where all the points are sensitive, that is to say, all initial conditions have at least one direction in which, if we think of a circle of uncertainty, there's always at least one direction in which that uncertainty tends to grow exponentially, at least initially. And so in order to cope with the situation, we calculate ensembles of initial conditions with a model. This is a Monte Carlo method, and what we hope to do is to find out that these models are locally low dimensional, which will reduce the complexity of the calculations that we need to do for purposes of data assimilation. And so I think that's it. So let me go over here to where maybe I can see you. Yes, I can hear you. Okay.
Any questions that stimulated in your mind or comments or? Oh, I'm sorry. Yeah, so if there are any questions or comments or anything that has stimulated in your mind or any connections with the other stuff you've been hearing, or? I guess it's probably sort of slightly awkward with you so far away.
I know.
Thinking about questions, but yeah. Do you want to go ahead?
You mentioned that from linear passage from linear system to nonlinear systems, when a point is unstable, when you force the system, practically every point becomes unstable.
Correct.
Well, in your graphics, only some points are becoming unstable, right, initially? Not every point.
Well, what we think of when you, let me see here, maybe I can try illustrating here if I can get back to, if I can find it here. It may have gone away. Okay, when you think about these spaghetti plots, let's see, maybe I can go back here. Okay, when you think about these spaghetti plots, this is really just a visual aid. But when I say that every point is sensitive, what I mean is that, if you take this particular weather model and you start it basically with any physically realistic initial condition, and you take another initial condition that's just a little bit different. Okay, so you start your weather model from two nearly identical states. No matter what state you pick, these forecasts will diverge. So after 14 days, the details of the forecast will be very different, and that's what I mean by every point being sensitive.
Thank you.
Does that answer your question?
Yes.
Okay.
There's another question. Jamal's coming up to the front so as he can be heard from the microphone.
Okay.
So here low dimensionality means attractor dimension of that nonlinear system, or in that sense, or which sense? That I have not understood.
Oh, how is this related to attractor dimension?
Yeah.
Well, that's a very good question. In the case of the weather model, I'm not sure I really know the answer. The global weather attractor, if you will, is something that in a model like this one, might sit in a 100 million dimensional space. Probably the full dimension of that attractor is quite high. I mean, when you think about an attractor, usually what you're doing is you're thinking about, if you will, the ergodic behavior. That is, what happens if we look at the weather over many, many years. And so the set of possible states that, that the actual weather would exhibit over a period of decades or centuries is pretty enormous. And so the dimension of that attractor in some abstract sense, even for the model itself, might be very, very large. So that's not really a number that would give us something that's really useful for forecasting purposes. It might be of interest for other types of investigations. What we're interested in the case of the weather is trying to make forecasts on the order of a few days from now. We're not trying to look centuries in advance. And so when I talk about this notion of local low dimensionality, what I mean is that over a relatively short forecast horizon, on the order of maybe a day or two, and again, not for the global forecast state space, but maybe over something over a synoptic region. So Texas is roughly 1,000 by 1,000 kilometers. This is basically 1,000 by 1,000 kilometers roughly. If we look a couple days hence, and we look at a region that's maybe this big, then in that sense, the dynamics are relatively low dimensional.
So I have a question about is this local low dimensionality being, so to say, demonstrated in some simple model? Not full-fledged
yes.
models, but so I didn't know the reference, but maybe you can, yeah.
What I'll try to do tomorrow is to do a little demo with MATLAB. But this Lorenz 40 model exhibits local low dimensionality, even though the state space is actually pretty complicated.
I want to make one comment that there's sort of a kind of a big jump in the middle of your talk when you're starting by talking about fixed points and sensitivity near fixed points, and then you're talking about the sort of big models and global or local sensitivity in these very big models. And I just want to emphasize and see if you agree with this statement, that you're not saying that there are fixed points all over the place which are sensitive in these big models, but rather that the notions of sensitivity near fixed points generalize to analyzing sensitivity near much more general trajectories in the big models.
Precisely.
Yeah, okay. So
you said it better than I did.
Yeah, so it's very important that there's quite a sort of big conceptual jump there, and that the first half is sort of laying the foundations for understanding what's happening in a much more complicated situation, right? But okay, is there anything else? So it's about 10 o'clock in the evening, I think, for Eric, is it, or even 10:30?
Yeah, but I'm awake, so.
You're awake. It's 1:23 a.m., but that's on the East Coast. That's
on the East Coast. We're 3 hours behind, so it's only 10:23, I think.
So you're at 10:23, right? So anyway, we really thank you for staying up and giving us this lecture, and let's thank Eric again, shall we?
It's my pleasure. Thank you for this.
Okay, and we'll see you same time tomorrow morning, is that right?
Same time tomorrow, right.
Tomorrow. Okay, thanks, Eric.
All right, everyone. I hope you have a good day today. Thanks for listening.